In this session, we'll see how to determine the value of xt and xq using a slip test. We know that in the case of the salient pole type of machine, the air gap is not uniform. Along pole axis, the air gap is very small, and interpolar axis, that is q axis, the air gap is large. Because of that, the reactance offered, that is what we are calling is the armature reactance, it is because of the armature reaction which is not uniform as in the case of non-salient pole type of machine in the case of the salient pole, because the air gap is not uniform. Therefore, across the pole axis, that is the d axis, the reactance is called as xt, which is the higher value, whereas in the interpolar axis, that is what we are calling as a q axis, the reactance of that is a quadrature reactance is small. Now we will review the concept once again. That is, in the case of cylindrical rotor, we know that the air gap is uniform throughout. Because of that, the distribution of the mmf along the air gap is uniform. Because of that, what you are assuming is the fictitious reactance of the armature reaction is uniform throughout. Therefore, you have got only one reactance, that is XA. But in the case of the salient pole type of machine, the air gap is not uniform along the pole axis, that is the d axis, and as well as in the interpolar axis, that is what we are calling is the q axis. Because of this non-uniformity of the air gap, the mmf distribution is not uniform throughout the air gap. That is, you can see here, that is along the d axis the air gap is very small, whereas in the interpolar axis the air gap is large. Therefore, the distribution of mmf is not uniform. Hence, the armature mmf, which is what we are affecting the main field, has got two different components, one along the d axis, that is the pole axis, another along the q axis. Thereby we are determining the value of xd and xq. And at the same time, we studied in the last session that the value of the xt is greater than the xq, that we have seen, because the flux produced along the d axis has got a higher value. Thereby, it is producing the more EMF effect. Because of that, the xt is greater than the xq. Then how to determine these reactances along the d axis and the q axis? Now we will see determination of the xt and xq by the slip test. Direct and quadrature axis reactance of salient pole machine can be estimated by means of a test that is known as slip test. It is called a slip test. We know that we are conducting the experiment on the synchronous generator. Synchronous means it is running with a constant speed of synchronous speed. But in the case of this particular test, what you are calling is a slip test, you are running the machine either less than the synchronous speed, little bit less than the synchronous speed, or you can run the machine slightly higher than the synchronous speed. That is what you are calling is, if it is higher than the synchronous speed, it is super synchronous speed, and if it is less than the synchronous speed, it is called as a subsynchronous speed. Okay, either for determining the value of the xt and xq, you are not running the machine to its rated speed, that is synchronous speed, but it is run at either slightly less than the synchronous speed or more than the synchronous speed. That is why it is running with the. Then, however, we are giving a supply to the armature winding, which is producing a magnetic flux, which is, we know that if you are giving a three-phase supply to the three winding, it is producing its own rotating magnetic field. But that rotating magnetic field has got a synchronous speed. Synchronous speed. However, the rotor of the alternator is running less than the synchronous speed. Therefore, there is a difference in the speed of a rotating magnetic field produced by the armature flux, and there is a rotation of the field which is running less than the synchronous speed. Therefore, the difference between the rotating magnetic field and the rotor speed is have got a difference. Therefore, it is called as a slip test. Therefore, the thing is that for determining these values, then you are running the machine either less than the synchronous speed or more than a little bit of the synchronous speed. So that there is a difference between the rotor speed and rotating armature flux. The machine armature is usually, in this case, what you are doing here is the machine armature, that is armature of the three-phase winding of the alternator is connected to three-phase supply. Here you are injecting the power to the armature. We are giving a three-phase supply whose voltage is much less than the rated voltage of the machine. What you have to do is you have to give the supply, a three-phase supply to the armature winding, but you have to apply such a voltage that it is less than the rated voltage, very less than the rated voltage, because we know that is a total impedance offered by the armature is very small. That is, it is comprised of resistance and reactance, but it is very small. If you are applying the rated voltage, and it will draw heavy current. Therefore, what you have to do is you have to run the machine little bit less than the synchronous speed, apply the small voltage to the armature of the alternator. The second step. While the rotor is run at speed close to synchronous speed, I told you it is close to synchronous speed, either it is little bit less or more than the synchronous speed, with the field winding left open circuited. That is one more thing you have to remember, that the excitation or the field winding is open, and field is connected, or it is a rotor in the case of the alternator, which is coupled to the prime mover. Then you have to run the rotor little bit less than the synchronous speed. That is, the field winding is kept open. Run that rotor with the help of a prime mover less than the synchronous speed. Then apply a smaller voltage to the alternator through ammeter and the voltmeter, so that you can observe the voltmeter and ammeter reading. You have to take the reading of voltmeter and ammeter reading. While the rotor is run at speed close to synchronous with the field winding left open circuited, as shown in the figure. That I will show the figure in the next slide. Since the excitation EMF is 0, the heavy current would be drawn by the armature if connected to the rated supply voltage. That is why I told you have to apply a smaller value of a voltage to the armature. The RMS current is minimum when the machine reactance is XD and is maximum when it is XQ. That is, we know that is the salient pole alternator is exhibiting, or it is possessing the two different reactances. One is the direct axis reactance that has got the higher value of XD and as compared to the XQ. Therefore, it has got two reactances. One is along the D axis, that is XD, it has got a higher value. The other reactance along the Q axis, which is got a lesser value. What he is telling this, the RMS current drawn is less when XD is more, because the applied voltage remains same. If the reactance is more, current drawn is the less. Therefore, what he is telling is the RMS current is minimum when the machine reactance is XD. It is quite evident because the XD is greater than XQ, and is maximum, it is a minimum when the XD, and it is a maximum when it is XQ. That is, we know that the XD is greater, therefore current is minimum, and XQ is minimum, therefore current is a maximum. Therefore, you are getting the current is minimum when the machine reactance is XD, and the current is maximum when the reactance is XQ, because XQ is less than XD. Then the simple setup for the slip test is, we have got an armature connected through an ammeter in one of the face, and you are connecting the voltmeter between the two lines. Therefore, whatever the voltage you are measuring is line voltage. While taking the calculation, you have to take this as a phase voltage. You not only line voltage, convert into phase voltage, and you have to do the further calculations. Okay, you are connecting the armature of the alternator through ammeter, and across the supply you are connecting a voltmeter. This is your armature. Then we have got a field winding of the alternator. It is across the winding we are connecting on the voltmeter. But however, the field winding, this is a field, the field winding is kept open. You are not exciting the field winding. That is, there is an armature. Then armature is connected through ammeter, and across the supply we are having a voltage V, voltmeter V, and in the field winding, your field winding is kept open, and across the field winding we are connecting on a voltmeter field. Then the machine is run with less than the synchronous speed by a prime mover. That is, we are running with a speed of n, which is less than the synchronous speed of ns of the alternator. Then what we are doing? We are giving a small voltage we are applying across the armature winding. Then it is drawing a current. Then there is the deflection in the voltmeter and ammeter reading, because we know that the current drawn, the ammeter, that is a pointer or the needle, is deflecting to maximum and minimum value. Here also maximum and minimum value, because when the reactance is xd, means xd is greater, in that case ammeter shows a lesser ammeter reading. That is a minimum value you have to note down. When the reactance is xq, which is less, therefore the current drawn is more, because we know that if you are neglecting the resistance, I is equal to V by X. That is, the V applied voltage remains the same here, but that is XD, that is the current, the XD, that is the reactance is more, that is the denominator is more, therefore the current is the less. Okay, that is, you note down there is a deflection of the ammeter, that is a maximum and minimum value. You have to note down maximum and minimum value of ammeter reading. At the same time, there is a deflection of the voltage, there is a maximum and minimum value. That is what you have to note down is, what you have to do is, the procedure is very simple. Start with the armature winding connected through ammeter and a voltmeter, and there is a field, and the field winding is kept open, and run the rotor with less than the synchronous speed. Apply the smaller voltage to the armature of the alternator by external source. Then you have to note on the ammeter and the voltmeter reading. Then we can observe here it is the applied voltage, and we have got along the q axis. Along the q axis, this is the terminal voltage, this is the line current waveform. To look into the, you can keenly observe here along the q axis, the voltage, the terminal voltage is minimum, whereas the current is minimum, because along the q axis, the current is more, because xq is less, therefore current is more, therefore the product of the reactance and the current, that is the voltage, is minimum here. Means, how to find out xq? It is a minimum voltage and the maximum current. Just you to observe for d axis, along the d axis, the current drawn is less here. You can see this is a current. The current drawn is less. Why the current drawn is less? Because the value of the reactance is more, therefore the current drawn is the less. Here the current is more, because along the q axis there is a reactance is less, therefore the current drawn is more here. Therefore you can observe there is a maximum current here, there is a minimum current here. Therefore you have to note on these values, that is a maximum current along the q axis, at the same time there is a minimum voltage, and at the same time along the d axis we have got a lesser current and the more voltage along the D axis. The same thing you have to note down, and you can see here the voltage at our machine terminals also varies cyclically and has a minimum value at maximum current and a maximum value at a minimum current that you are seeing here. For a maximum current, you have got a minimum voltage. For a minimum current, you have got a maximum because of the effect of XT and XQ. Therefore, the machine reactances can be calculated by using the voltmeter and ammeter reading. That is, XT can be calculated as, that is XT, it is a maximum voltage divided by minimum current. That is Vt max, that is the ammeter reading you have to note down, that is the maximum voltage. This maximum voltage that is seen by the voltmeter, maximum voltmeter reading, it is a deflecting. Therefore, maximum deflection of the voltmeter you have to note down here, that is Vt maximum. However, this is a line value what you are noting down from the voltmeter in the diagram. Therefore, you have to divide by root 3 so that you will get the per phase voltage. Therefore, Vt max divided by root 3 is the phase voltage. Then divided by Ia minimum, that is, this is Ia minimum. Ia minimum. Therefore, there is a deflection of the ammeter from maximum to minimum. The minimum value of current you have to put here. Therefore, maximum voltage by minimum current, that gives the XD. Here I am taking divided by root 3 because whatever the voltage, maximum voltage you are noting down, it is line to line value that I am converting into the phase value. However, in the case of star connection, the current either line or a phase remains the same. Similarly, in the same manner, the XQ can be calculated as, it is a minimum voltage by maximum current. Minimum voltage divided by maximum current. Therefore, it is Vt minimum, that is a minimum deflection of the voltmeter reading you have to note down, divided by root 3, that gives the once again the phase value of the voltage divided by the maximum current, that is the maximum current, that is a minimum voltage divided by maximum current, that gives the value of xq. This is how we have to determine xd and xq of the alternator, that is salient pole alternator. Okay, the procedure is very simple.